Hi, my name is Jerome. We are pleased to present. ZKM is here in Denver. We are pleased to present our implementation of a modular zero-knowledge virtual machine using Lookups. My name is Jerome. Stefan is on my left. Lucas also helped prepare the presentation, but he isn't here. Let's start with the concept of a proof of knowledge. For some computational problem, a proof of knowledge is a protocol that allows a prover to convince some verifier that it knows a valid solution for some specific problem instance. So an example is if you have the Hamiltonian cycle problem, you have a graph and you want to know if there exists a cycle, if there exists a path that will visit each vertex of the graph exactly once. So the context that we have is we have a prover, we have a verifier, and the prover says, well, I know a solution for this instance of a Hamiltonian cycle, and it provides the proof. Now, for every proof of knowledge, there exists the trivial proof, which is just the answer, the full answer. But for some contexts, some applications, this is not a good idea, because there are two contexts. The prover might prefer to keep the solution a secret. So maybe the prover, if we have a larger example, the prover might prefer to not reveal exactly what the secret is. And another context is that the resulting proof may be too long for the verifier to check. So these are two different extensions of the proof of knowledge. The first one are really called the zero knowledge proofs. So the zero knowledge proof is the property that you have a proof that does not reveal information about the solution for a given problem. And this is often implemented by performing a randomization, a verifiable randomization over the problem instance, and then show that you know a solution for it. So in the example here, we have permuted the original instance, and we show in the permuted instance that a cycle exists. So this would be an example of a zero knowledge proof. On the other hand, we can have different criteria. We may want that the proof is short, because in some contexts we have that the prover is much more powerful than the verifier, and so the verifier doesn't have the computational capacity to process the proof and to verify it. So what we want is we want what are called succinct proofs, in which the verifier only has to flip random coins, perform some checks on the proof that the verifier sent, and then accept or reject. So what we are doing in the case of a succinct proof is we are simplifying the work of the verifier at the cost of putting the burden on the prover. It's it's a setting in which we have maybe the prover is a strong cluster and the verifier can be a cell phone. Or we can have a context in which the prover is off-chain and the verifier is layer 1. Now the context that we are applying this proof of knowledge is the context of verifiable computation. So in verifiable computation, there is one step before the proof of knowledge, because it's the verifier who is now the weak user and is asking to the prover, I have this function X, I have this function F, I have this entry X, please compute f of X for me, resulting in Y. So the idea in verifiable computation is that the prover will compute y, which is the f of x, and in addition to giving the result, it will also produce a proof w, which shows that the value of y is indeed correct. And so important is that we want this proof to be short, because we want the verifier should have very little work to do. Now, in the context of blockchains, these proof of knowledge, they should be succinct, as I said. They should be non-interactive. We want to avoid interaction between the prover and the verifier for a couple of reasons. And they can be zero knowledge. So they can provide privacy, but they don't have to provide privacy. And so the problems to which we apply these proofs of knowledge, they can be the transition function for layer 2, which are sort of ZK rollups, the execution of smart contracts, which is the zkEVM. So the smart contracts are then written in Solidity, and we have the EVM that verifies the execution of the contract. And we can have other programs, which are the zkVM. So we have a program, in our case, it's a MIPS program, and we want to verify the execution of the MIPS program. And the technology that's being used for this are SNARKs, which stands for Succinct Non-Interactive Arguments of Knowledge, which optionally can be zero knowledge or not. So how do SNARKs work? Well, this is a little bit high level, but it gives a little bit of the flavor. A SNARK does something very surprising. A SNARK will translate everything, every computation, into a polynomial. And this polynomial is expressed modulo some large prime number, maybe a prime number with 64 bits. Because I don't know, there's a lot of mathematics behind this, but if you have a prime number, you can add and you can multiply, and that means that you can define, have a meaningful definition of what a polynomial is. So having a finite field, well, it's easy to add, to multiply, or to exponentiate modulo this prime number. For bit operations, things are a little bit more difficult. So the first line that you see there, the bitwise operation, is a test to see that the element in modulo the prime number is 0 or 1. And then we have expressions for the OR operation, the AND operation, and the exclusive OR operations. And we also have a way to combine, to batch a lot of polynomials together without increasing the degree. This is an important aspect, because what we do if we want to verify that P of x is equal to A and P of y is equal to B, then we make a linear combination of this. Well, so the linear combination is of Px minus A times alpha, and then Py minus B times beta. And so this value should be 0 if this condition is satisfied. So that means that using this encoding, this coding is also called arithmetization. It guarantees that any knowledge can be proven. We can do the succinctness, and the verifiable randomness. We can make the proof non-interactive using Fiat-Shamir transform. Nevertheless, some properties are difficult to verify just using polynomials, and this is why we use lookup tables. So how does the SNARK work? We have the original problem. We transform it into a MIPS execution trace. We then, the execution trace, we have the register, we put it into a polynomial, and the opcodes, we put this into a polynomial. We combine the two, and this will give us polynomial commitments and lead to random polynomial commitment evaluation. And now, Steven is going to give all the details.
Okay, thank you. Let me go through all the details with an example. Okay, given that the Golang, the high-level language can compare it into MIPS, and we got a sequence of the MIPS instructions, like the add instruction would be add register 5, register 6, and write the value back to the register 7. Okay, and for the write table, it's when we execute each instruction, we got the value of each register. Yeah, and we go through all the instructions. We finally got a trace table, including all the values we go through. Okay, after we got this trace table, then we need to apply some kind of technology like the continuation. That means we split the whole instructions or the whole table into different segments. Okay, so each segment may have fixed instructions, and then here we need to, because we have a trace table, we need to apply the constraints on each row or cross the different row. So first is we convert each row into a constraint polynomial, like for the row I, the Ci R5, R6, R7 equals to R7 minus R6 and minus R5. Okay, we call it constraint polynomial. So now with the instructions sequence, we have different constraint polynomial. And on the other hand, we also have a trace polynomial. That means the R1x, R2x. That we want to commit for the trace, for the execution trace. Okay. As I mentioned, we need to apply the constraints on the execution trace. So, because the different instructions have different constraints, so we split the instruction as put the type into different modules. Like we have an arithmetic module, CPU module, logic module, and a memory module. So different module has different constraints. Okay, and of course we also need to make sure that the values they shared, like the different columns, are identical. Okay. So after we got the modules and we have the trace table, we begin to prove each module. Okay, so for the proving, we just use a stack. That means we commit the trace by fly. And then we actually got different stack proof. Okay. So because finally we need to verify the final proof on layer 1, so we need to join the different modules proof by kind of proof composition. Okay. So yeah. Okay, I think I would go this quickly because it's just saying that we have different modules and we produce the proof for each modules by the stack. So for the stack, I think we will not go through the details. It's just it's kind of the Mocha proof, Mocha commitments. Each we mapping the trace polynomial into the Mocha proof, Mocha tree leaf, and then calculates the Mocha roots. And of course, we use the multi-query to sample the to open the some points. Okay. Okay. So that's what say we join the different proof into one. That's we use the proof composition. Yeah. For the proof composition, actually we have different segments. First we generate the stack proof for each segment, and then we yeah. So why we say the root proof here? Because we have different table, different trace table. So we actually have different have multiple stack proof for even one instructions. So first we need to combine. We need to combine the different stacks into one proof. Okay. So that's why I say the root proof is the proof of root circuits of all the stacks, and then we aggregate the root proof. Okay. So the aggregate proof would be the aggregation circuit over the two different root proof. And finally, as we know, the stack proof is quite large. It's maybe reach up to 4 megabytes. So we need to use some other, snag algorithm to compress the proof. So that's here we use a group 16, and we can achieve a constant proof size about 200 bytes. And that's demo for our proof composition. So yeah, so it's quite easy if you can write a Go nom program. Then use the Go compiler to compile it into the MIPS. It's quite simple. And then you can use our examples in our GitHub repo to split the MIPS into different segments, and then generate the final proof for all the segments. Okay, so that's all.
Okay. So we'll take any questions offline. Okay, thank you very much for your attention.
Thank you very much.